Hello, everybody. I hope you're doing well. Welcome back to another video reviewing your probability and statistics fundamentals. It's so great to be with you today on a Thursday evening. And today in this video, we're going to be talking about confidence intervals. So, as you may recall in the previous video, we were exploring the idea of sampling distributions and how, when we discovered that if I sample from a population a bunch of times and I want to estimate, say, the mean or the proportion, we can plot a distribution of these sample means and sample proportions, and we get what's called a sampling distribution. And we found that a powerful theorem is that if we have a large enough sample, we could assume normality given that the normality checks pass. So in the case of means, we saw the central limit theorem, right? So if we have a sample size at least 30, then the sampling distribution of the mean can be thought to be approximately normal, regardless of what the population distribution looks like. And in the case of proportions, we use the np greater than or equal to 10 and n times 1 minus p greater than or equal to 10 like checks to test for normality when we're estimating sampling distribution of proportions. So we've talked about being able to estimate probabilities of getting sample means and sample proportions within certain thresholds above or below. But in this case, we're going to talk about confidence intervals. And this really hinges on the idea of estimation. So within statistics, right, when we collect samples to estimate information about the population. So if we want to figure out the mean of a population and we don't have time to take a census and essentially go and sample everybody in the population, we want to be able to see how we can use our sample to estimate, say, the population mean. So in this video, we're going to be talking about a tool in statistics that statisticians use to estimate the population mean given a sample mean. And that, my friends, is called the confidence interval. So I know what you're thinking, right? Confidence intervals might sound like, some old hokey pokey phrase, and it might seem a little confusing, but let's talk about it a little bit slowly, right? So what is a confidence interval, right? So I guess to start, right? We have our sample, right? And we have our sample mean, right? And the question is, how can we estimate the population mean? So I can't say like, if I get, say, a sample mean of 60, right? I can't say like 100% the population mean is going to be like 58, right? I don't know for sure, right? Like what the actual population mean is because I don't know like how I've sampled. Maybe I might have not picked a representative sample and I didn't know beforehand, right? So what we could say is maybe I might say that the population mean is between, I don't know, 56 to 65, right? And if there was a way of saying I am X% confident that the population mean lies within this interval, then I have some kind of heuristic to say, okay, with some degree of certainty, I can say that my population mean is within this interval, right? I don't know what the exact value is, but I can say maybe within some window, right? Or some interval. Maybe this is where the population mean lies, right? So confidence interval gives you a tool to do that, right? And with that being said, let's divert our attention to the diagram here shown on the right-hand side. So let's take a common example, right? So you have a poll in a magazine, right? And in a poll, right, we want to figure out like who's the top favorite famous person, right? And we see that 46% of the vote goes to John Cena, right? And obviously there's going to be a margin of error of 3 percentage points. And margin of errors can happen because maybe like I pull different subpopulations, right? Or maybe I took the poll multiple times and maybe different people answer the poll. There's lots of things that could happen, but we get some margin of error of 3 percentage points, right? So if John Cena has 46 percentage points of the vote with a margin of error of 3 points, then you'd most likely conclude that John Cena likely has between 43% and 49% of the vote. So hopefully you understand how we can come to that conclusion. This is our intuitive understanding of margin of error, right? It means that John Cena has maybe less than 3% of 46 or more than 3% of 46. So we have this, window of possible percentage points in which John Cena has the vote, right? So between 43% and 49% of the vote goes to John Cena. Now here's where the confidence level gets interesting. So I take a sample, right? And my sample gives some estimation of the mean population who votes for John Cena. So that's going to be sample 1, right? And I do another sample here, and I get like this interval, right? That estimates, the proportion that John Cena has for the vote, right? And I know we're talking about proportions here, but we're going to be talking about means, but I just want to build an intuition based on something you know. And then maybe we take another sample and it gives you this green interval here, right? And you might take another interval here in blue, right? And this sample gives us this estimation of the population parameter, right? So remember that parameters describe populations, statistics describe samples. But let's say that John Cena himself says that, oh, I actually have this percentage of the vote, right, within the fan base community. So what do we notice here? If we draw a line like slicing through here, right, these intervals, we see that the green interval, the black interval, and the red interval like contain this, blue line, right? But this blue interval here doesn't contain a blue line. So we can say in this case, 3 out of the 4 samples contain the true parameter, right? And this is what confidence intervals tell you, right? So as you can see in this below figure, right? We collect 40 samples, right? And we basically highlight what are the intervals in which the population parameter can lie. So maybe in this sample, right, up here, right, this is our interval that estimates the proportion of people who like John Cena. We get another sample, we get this estimate, and then we get this estimate from this sample, and then this estimate from this sample. And you repeat the process, right, for how many ever samples you want, right? But let's say that John Cena has 44% of the vote. So in this case, my parameter value is actually this green vertical line, right? So as you can see in this drawing, among 40 samples, right, we see here that 38 of these samples, right, contain 44% in its interval for estimating the true proportion of people who like John Cena, right? But these red intervals here, right, do not contain the green line, right? As you can see, this interval right here is not touching the green line. This interval here is not touching the green line. So we see that 38 out of 40 samples um, depict, or contain the true proportion of people who like John Cena. And this is what we call the confidence level, right? So the confidence level is the proportion of samples that contain the true value of the parameter, right? So we're gonna have this confidence level concept come up a lot, right? And by adjusting the confidence level and adjusting our sample size, we will see that this affects the intervals we're getting, right? So let's go back to the part where I was talking about margin of error, right? So an interval is going to be some starting value, right? Plus or minus some margin, right? And this margin can come from lots of things, right? It could come from the way you sample. It could just come from the way the population is as a whole that you're sampling from or studying. But all confidence intervals have this general format: a starting value plus or minus a margin of error. Now let's formalize a little bit, right? Since we're talking about means, what do we remember from our discussion for means? So we have x bar as the sample mean, right? We have n as our sample size. We also have S sub x, which is the standard deviation of the sample. And sometimes we might know the population standard deviation, but let's just say we know the sample standard deviation because that seems kind of relatively easy to calculate on Microsoft Excel. So we have the sample standard deviation. And we will also have something called the confidence level, right? This is what we need to build our confidence interval, right? And if you recall from our discussion of sampling distribution of means, right, we learned that if the sample size is at least 30, right, then we can approximate the sampling distribution of the mean with a normal distribution. So based on normality, right, we might have either a z or a t statistic. So z star or t star might come in handy. And we'll see that the z star or t star values are influenced by the confidence level. So let's do a bit of drawing. So let's suppose we do have a large enough sample size, right? And let's assume, for the sake of simplicity, that we can assume that the sampling distribution of the mean is a Gaussian distribution, right? So we have this bell curve, right? This center value is going to represent the sample mean, so x bar, because this is the basis in which we're going to build our interval off of, right? This is like the starting point, right? So we're going to center at the starting point, right? And if we say that there is a, if 95% of samples include include the true population mean, in this case, we define that the true population mean is simply the sample mean, right? by the definition of sampling distribution of the mean, right? So we want to figure out what are the proportion of samples that would result in containing this X bar, right? And that's what the confidence level is going to represent. So if we have a 95% confidence level, what that means is the area right here, right, is 0.95. So this red area is actually going to be 0.95. And since we have a normal distribution, we should be able to find this z-score here, right? And we can find the z-score easily, right? So the one thing to keep in mind with confidence intervals is that confidence intervals like go in both directions, right? So remember how we have a starting value as our like basis, and we go plus or minus the margin of error, right? So that's why the area shown in red is kind of what we're going to be getting, right? And the area between these two z-scores right here is going to represent the confidence level, right? And this seems to agree with the above interpretation that I mentioned with the John Cena example. So this is kind of what's going to happen, right? So we take our distribution, right? We use the confidence level we were given this in the problem, and we basically have to find the z-score, right? Such that the probability, right, of negative z less than or equal to z, so I'm going to call this z naught, less than or equal to z naught, equals the confidence level, right? So this is essentially solving a z distribution problem, right? And we'll use our z table to do this, right? So, and this will be made more concrete in an example problem, but I just want you to motivate like what the purpose of the confidence level is. So now that we have the confidence level, right? Given the confidence level, we can identify, this z naught right here, right? These z-scores, right? Such that the area in between is the confidence level. So now with the z-score, right? The z-score represents the number of standard deviations from the mean, right? So if z was, say, I don't know, 1.96, then this point here, if this was 1.96, you're going 1.96 standard deviations to the right of the mean. But what is the standard deviation of a sampling distribution of the mean, right? So standard deviation, right, for sampling distribution of the mean, right, is going to be S sub x over root n. Right? And we saw this in our previous video when we were talking about sampling distribution of means. So now that we have our standard deviation, we have our confidence level, and we have our starting point, let's actually build the formula for the confidence interval of the mean. So to calculate the confidence interval for sampling distribution of means, we take the sample mean, plus or minus, and our margin of error is going to be whatever this distance is. But this distance is technically the number of standard deviations times the standard deviation itself, right? So based on our confidence level, we will get a z star, right? We're assuming normality here that the central limit theorem works. And this z star represents how many standard deviations we're going to go from the mean, right? So we need to figure out, we have how many standard deviations, right? But what is the standard deviation itself? Well, it's just going to be S sub x over root n. So now we have the formula for the confidence interval for sampling distribution of the mean. Now, if the central limit theorem doesn't pass or we get our small sample size, we'll just simply modify the formula to use the t distribution. So this is the case, this formula here is going to be the case where we don't assume normality, right? But the same idea holds, right? This is why the t-distribution is kind of a really neat idea for relatively small sample sizes. So these formulas are equivalent. It's just, do you use the z-distribution or the t-distribution when figuring out your z or t-score to construct a confidence interval? And that's dependent on the normality check. So we have these formulas for calculating the confidence interval given a sample mean, given a confidence level, given a sample standard deviation, and a sample size. So one thing I'd like to pay attention is this term shown in green right here, this dotted line, this term is what we call the margin of error, right? And as you can see here, this is the start, this x bar is our starting point, and the plus or minus is representing our margin of error, right? So z star times sx over root n is the margin of error. And likewise, this is our margin of error in the case of non-normality. So yeah, this is just something important to highlight. And we will be talking about margin of error a little bit more in depth and see what we can do with it. But let's jump into the examples. So example 1, suppose we want to rent a unfurnished one-bedroom apartment in Durham, North Carolina next year. We know that the mean monthly rent for a random sample of 60 apartments advertised on Craigslist is $1,000. And we're going to assume that the population standard deviation is $200. Let's construct a 95% confidence interval. So for example 1, what do we know? We know the sample size is 60. We know that the population standard deviation is going to be 200, right? So in this case, sigma is 200, right? Because sigma represents the population standard deviation, S sub x is the sample standard deviation. We also know that the sample mean is $1,000, and the confidence level of interest is 95%. So what do we know from the sample? We know that 60 is greater than or equal to 30, right? So by CLT, sampling distribution is approximately normal. Okay, so now that we know that it's approximately normal, let's construct a confidence interval, right? So we know that the confidence interval, in this case, we're going to use the equation with the z star, right? So we're going to have x bar plus or minus z star s sub x over root n, right? And in this case, our s sub x would be sigma, right? Because we know the population standard deviation, right? So we know x bar, right? We know S sub x, or sigma in this case, and we know the sample size. What's left is to find z star, right? So since we have a normal approximation, right, we know that this area in red will be 0.95. So if we have some z naught right here, right, in these places, right, I want to find the probability that, we're having a z-score in between negative z naught and z naught inclusive, right? This probability is 0.95. But what do we know? In our normal distribution, right, it's symmetric, right? And our table will give us this area in green, right? So what we need to do is we need to find the probability of getting a z less than or equal to negative z naught. And the probability we want to find, in this case, is going to be 1 minus 0.95 divided by 2. And this is because of the symmetric nature, right? So I want to find the z naught such that the probability of z less than or equal to negative z naught is equal to 0.025. So let's take a look at our z table, right? I'm going to look for the z-score corresponding to the fact that this area right here in gray on your left is 0.025. So when we scroll down a bit, we will see that 0.025 happens at the z-score of negative 1.96. So z naught is going to be equal to 1.96. So we have our confidence interval ingredient. We have our z stars. So the confidence interval is going to be 1,000 plus or minus 1.96 times 200 over square root of 60. And evaluating this out, our interval is going to become 1,000 minus 1.96 times 200 over the square root of 60, comma 1,000 plus 1.96 times 200 over the square root of 60. And this is going to equal, let me punch this into my calculator real quick. So we see that the lower bound is 949.39 approximately. So our interval will be 949.39, comma 1050.61. So from this interval, what this means is there is a 95% of samples we get will capture a population mean rent between 949.39 and 1050.61, right? So we're giving kind of an estimation of where our population mean rent will lie, and it's going to lie in between this interval, right? And the confidence level of 95% means that 95% of samples will encapsulate, the true population mean rent, which lies between 943.39 and 1050.61 as our approximation, right? So this is our confidence interval for the rent problem. So hopefully that makes a lot of sense. We'll move on to example 2. So example 2 is a very similar idea, right? So we want to study sales of cameras at a camera shop. We have a sample of 15 randomly selected sale items. We find that the mean revenue among those samples is $5,600 with a standard deviation of $500. We're going to use a 90% confidence interval for this scenario, right? So what do we know? We know that n is 15. We know that the mean is 5,600. We also know that the standard deviation of the sample is 500. The confidence level we are using is 90%. So what do we notice here, right? Well, we know that 15 is less than or equal to 30, right? So we cannot use CLT, right? And we cannot assume normality here, right? So the sampling distribution is not approximately normal by the CLT. So we're going to use the t distribution, right? So we're going to use this equation right here. We will be using this model here. So confidence interval is x bar plus or minus t star s of x over root n. So what do we know about the t distribution? We know that the confidence level is 90%, right? So what that means is the area between this negative t naught and t naught right here, this region is going to be 0.9. So I want to find the t naught such that this area in green is going to be 0.05. Now, how did I get 0.05? Well, we know the area outside the red region in total is 0.1. And because the normal distribution is symmetric, we know we distribute the remaining area evenly, right? So this green area here is 0.05, and so is this region. This is also going to be 0.05 by the symmetric nature of the t distribution, right? So basically, we want to find the t-score such that the probability of that t is less than negative t naught is equal to 0.05. And in our t distribution, we know the degrees of freedom is the sample size minus 1. So the degrees of freedom in this case is 14. So we're going to use our t table, look for degrees of freedom 14, and I'm going to look for the scenario where the probability right here is 0.05. So we're going to go degrees of freedom 14, and at 0.05, we see that the t-score is 1.761. So we know that t star is 1.761. So our confidence interval plugging into the formula is going to be 5,600 plus or minus 1.761 times 500 over the square root of 15. So now, from punching this into the calculator, we're going to get the following as our interval. So it looks like our confidence interval is 5,372.66 2, comma 5,827.34. So this is our 90% confidence estimate of where the true mean revenue lies, right? And with a 90% confidence, basically. So this is how you do example 2. It's again the same procedure as problem 1, but we're using the t distribution instead of the z distribution because the central limit theorem doesn't work in this case. So that takes care of examples 1 and 2. Final example I want to touch is on example 3. So we're going to revisit example 1 where we're studying Craigslist rents. And we want to answer a different question. How large of a sample is needed to estimate the population mean with 90% confidence? And we're assuming the population standard deviation of $200, just like example 1. So what do I mean by this, right? We want to estimate the mean rent, the population mean rent with 90% confidence. And we want to do this, within $50 of a margin of error. I forgot to add that into the question, right? We want to estimate the true mean rent by $50, by give or take $50, right? So what is this other word for give or take that we've discussed, right? So this give or take, that we've discussed is a fancy way of saying the margin of error, right? So we know that the margin of error in this example is $50, right? Because we want to estimate our mean rent within $50 of accuracy, right? So our margin of error is $50. We know that the confidence level is 90%, and we also know that the standard deviation, right, S sub x is $200. The only question that remains is, what is n? So we have our confidence interval for the mean, right? And when we look at our formula carefully, right, which is the term that's corresponding to the margin of error? It's this term that I've circled here in the green dotted lines, right? And because we're assuming normality here, right, we know that the margin of error, right, is going to be equal to z star, right, times s of x over root n, right? Now, in this case, since we have a 90% confidence level, right, this area shown in red is going to be 0.9, right? And I want to find, and then we have these z naughts, right? So I want to find I want to find what z naught I need to get such that the probability of z less than or equal to negative z naught is 0.05. And it's the same argument as we've done earlier. So hopefully this makes sense, right? Because this green area must be 0.05. So we go to our z table, right? And we look for the z-score corresponding to this gray area of 0.05. And when we look a bit carefully, we see that that seems to happen at around negative 1.64, right? So it looks like here that z star is going to be 1.64, right? So we know the margin of error is $50. We know the z star is 1.64. We know the sample standard deviation is 200, right? And all we have to do is solve for root n, right? So if we do a little bit of algebraic manipulation, right, we see that 50 over 1.64 times 200 equals 1 over root n. When we square both sides, right, we get that 50 over 1.64 times 200 whole squared is equal to 1 over n. So what that implies is that n is going to be equal to 1.64 times 200 over 50 whole squared. So this is what we're going to do to find the sample size, and we punch this expression into our calculator. So we see 1.64 times 200 over 50, and when we square, our sample size n is approximately 43.0336. All right, so let's talk about some closing remarks, right? So we know that the confidence interval for estimating population mean, given that we have a sample of decent size and it satisfies central limit theorem, we have this equation, right? So what can we tell, right? Suppose we increase the sample size n. What's going to happen? Margin of error is going to decrease, right? Because the denominator will get large, right? As n grows, root n will get bigger, and since root n is in the denominator, this whole term right here that I've circled is going to get smaller. So when the margin of error is smaller, right, we have a narrower confidence interval, right? So it goes to show that sometimes a large sample size is pretty good, but you have to trade that off with like the cost and the hassle involved in getting such a large sample. But statistically, right, getting a large sample is a good thing, right? Because we decrease the margin of error, we get a narrower and more precise confidence interval, right? Suppose we up the confidence level, right? So when we up the confidence level, what's happening, right? Well, if we have our distribution, right, this area in red is getting a lot bigger, right? As the confidence level goes up. So what's going to happen when you see your Z table, right? If you compare 90% confidence interval to 95% confidence interval and compare what the value of Z star is, we're going to see that Z star is going to go up. And since Z star will go up, we know that the margin of error will go up, right? Because that circle term right here is going to get bigger. So this will actually cause a wider confidence interval because the margin of error is getting big. So that's something important. And the standard deviation of the sample can also play a role in the confidence interval, right? Because if we have a lot of uncertainty in our sample, that might correspond to high spread or high standard deviation in our sample due to the uncertainty of maybe the population, right? So if the standard deviation sample is larger, this margin of error gets larger, the confidence interval will get wider. So this is just a few things I want you to keep in mind. There's obviously a trade-off with getting a large sample size versus having a high degree of certainty in estimating your population parameter, right? And these are the trade-offs you have to weigh basically when you are in the real world. So hopefully this video helps give an overview of confidence intervals and especially in the case of means. So next video, we'll be discussing confidence intervals, but for proportions. I expect the next video to be a bit more brief in that the formulas or idea is going to be pretty much the same. It's just the equation will be a little different because we're talking about sampling distribution proportions. And in fact, you might be able to build the equation for the confidence interval for sampling distribution proportions, right? Based on what we did in the previous video when we were discussing sampling distributions. So with that in mind, I'll leave you to think about that. But thank you so much for tuning into this video. It really means a lot. Have a good rest of your Thursday evening and hope to catch you guys later.